Hello. In this video, I will introduce a tool called PyPANDA that was released at an academic conference just a few weeks ago in a paper titled PyPANDA, Taming the Pandemonium of Whole System Dynamic Analysis. And essentially what this tool does, what this academic work presents, is an interface to the interface from Python to the Panda reverse engineering tool. And this will be a somewhat condensed video in that we will do quite a few things. And the first thing we will do is we will look at, just go over the paper, some specific points in the paper. Then we're going to look at the source code for some of the examples of using PyPANDA. And specifically, we will look at how a generic unpacker is implemented with PyPANDA and how you can interface whole system analysis, so like out-of-the-box analysis with Ghidra as well. And then we're going to run this experiment to see how it actually works with a UPX-packed executable. And finally, we were lucky to get an interview with Luke Craig as well, which is the first author of this paper. So we're going to ask him just a few questions about Panda and hear a little bit different insights that may not be available in the paper. Okay. So let's get started. And the first thing I want to do is just look at the abstract a little bit. And we can see here that it says, when working with real-world programs, dynamic analysis often must be run on a whole system instead of just a single binary. Existing whole system dynamic analysis platforms generally require analysis to be written in compiled languages, a suboptimal choice for many iterative tasks. Furthermore, these platforms leave analysts with a split view between the behavior of the system under analysis and the analysis itself. In particular, the system being analyzed must commonly be controlled manually while analysis scripts are run. To improve this process, we designed and implemented PyPANDA. So they have implemented this system PyPANDA in order to improve on this task of doing iterative analysis. So instead of having to write your analysis tools in compiled languages, which is not the most optimal choice for doing iterative analysis, they want to implement this PyPANDA, which is this interface from Python to Panda, as they write here, a Python interface to Panda dynamic analysis platform. So they want to improve on this iterative analysis approach by making it more accessible to write analysis scripts with Python, and then also to improve on the analysis experience by removing this split view problem in terms of having a split view between the behavior of the system under analysis and the analysis itself, where some sort of analyst must commonly be controlled manually. And it should be said here that what they propose as well is that they demonstrate the capabilities of PyPANDA by way of 3 different examples. In particular, it says the capabilities of PyPANDA are demonstrated by using it to dynamically evaluate the accuracy of 3 binary analysis frameworks, track heap allocations across multiple processes, and also synchronize state between Panda and a binary analysis platform. And this third example here is the one that we are really interested in terms of synchronizing the state between Panda and a binary analysis platform. And this is the example that we will go through in order to get familiar with PyPANDA. So let's go down a little bit in the paper to look at the section where they describe this example. Here, extracting and transferring packed executables to Ghidra with human-in-the-loop entropy analysis. And if we go a little bit up, we can see that this example is placed in the section called evaluation. And it should be said here that the paper that I'm going through is the preprint of this paper, and soon you will also have a camera-ready version, which at the end of the day will be somewhat similar to, very, very similar to this paper, but perhaps a few typos and some other things will be changed. But it should be released in just the next few days. Okay, so under the evaluation and going to this third section on extracting and transferring packed executables to Ghidra with human-in-the-loop entropy analysis, we're going to go through that example, and I will just cover what this example does. The core idea behind this unpacker is described in this paragraph on page 8. So it says, In this section, we will discuss a PyPANDA script which records a whole system running a packed binary. The script is given a process name to consider and computes the entropy of all segments of memory throughout the life of the process. As it performs this analysis, the script spawns a Python Flask server, which serves as live updating graphs the entropy of the process memory. If a user is interested in looking at the program state at some point along the graph, they may click on the point. The Flask server will receive their selection and spawn a new process which replays the recording up to the point of interest, extracts all mapped virtual memory in the process, and transfers it to static analysis platform Ghidra through the use of Ghidra Bridge. A Python module built to allow remote procedure calls into Ghidra. So that's the Ghidra bridge they describe. It does all of this, including generating the recording in fewer than 200 lines of Python. So to summarize this, essentially what this script will do, the generic unpacker, is it will execute a packed executable inside of our virtual machine in this whole system that we will be running, and then it will look at the memory, the virtual memory of a specific process in this virtual machine, and then it's going to calculate the entropy of all segments of this memory. And that means we will get some type of value, say 5.0 or something like that, which corresponds to the entropy of the data in this process. And this will then be displayed in a web server developed in Python Flask that will give us an XY coordinate where the Y coordinate is the entropy value and the X coordinate is kind of like how far in the execution in the recording how far in the recording we are relative to the state of the virtual memory. Now, the main point here is that you can, by looking at the entropy of the virtual memory, you can kind of tell if the memory in the process corresponds to an unpacked binary or it corresponds to a packed binary. And this is really the key idea behind this unpacker, is to use entropy analysis as a way of determining when unpacking has occurred. And this script will then display these graphs to us, as we see right here, where we have entropy on the y-axis and we have the number of instructions replayed here on the x-axis, and we will then be able to click on either one of these dots. And when we do that, this PyPANDA unpacking script will do a replay of the execution, and then at the given instruction count where we clicked, it will grab all the virtual memory of the process, take it out of the virtual machine of the Panda recording, and then it will throw it into Ghidra so we can analyze the binary or the process memory in a static context rather than by way of or just that we can analyze it in a static context. And this is really valuable because we can automate the process of, in a very general manner, automating the process of reaching the state where the program is unpacked, and then we can transfer all of it into Ghidra so we can analyze it in a much more improved way than, say, having no Ghidra. And that's really what this and it can do this in just 250 lines of code. So one of the main points here is also it can do this type of analysis in a very, very lightweight programmatic way. We don't have to do a lot of coding in order to create such a general analysis tool. Okay, so let's try and look a little bit at the code for this example. So the code for PyPANDA in general. So all of the code that is related to this Panda platform for architecture-neutral dynamic analysis is available in this umbrella repository on GitHub. And inside of the Panda main repository, we can navigate to the PyPANDA code by going down to the Panda folder here. We can then go into Python, and here we have all of this, essentially all of the code related to PyPANDA. But if we want to go through the examples of the paper, we have to go into this repository, BAR 2021. So they have made it the authors have made it extremely simple for us to actually reproduce the work. that is presented in this paper. And we can see in this repository, we have four folders, and 3 of them corresponds to the 3 examples in the evaluation folder. So in the evaluation section of the paper. So in the evaluation, we have this dynamic Oracle IR testing, which corresponds to the work in this folder or the content in this folder. And then we have another example, which is heap monitoring, which is this heap tracker right here. And then we also have the code for this dynamic, so like general unpacker, which is right here. And the code itself is very extremely easy to reproduce. Essentially, they have wrapped everything in Docker containers, and I'm going to show you exactly what to do in just a moment. But we can see that with just say 5 different commands or so, we are able to reproduce the work of the unpacker. But let's look a little bit about what's going on in the unpacker folder. And let's actually drag this one over here and just look at, in order to reproduce the work in the unpacker, we first have to clone this repository. We have to build the Docker image, and then we just have to run this Docker image, which will start a container, as far as I'm aware, which will start like a shell in the Docker container. And then we have to issue these 3 commands. So navigate into the Docker folder and then run this Python command, make recording, with an argument called bash. And then we have to afterwards run this other Python command, namely pyunpacker.py. And then we can connect, we can use Ghidra to connect to, we can connect whatever work is happening in our unpacker to Ghidra and start doing the unpacking. So it's really just 2 commands we have to issue, namely unpacker as well as make recording. And now when we are going to look at this code, we are going to see how the code of PyPANDA actually is. So going through this example will both give us a good idea, we will understand how this exact kind of unpacker example works, but we will also use it as a way to get more comfortable with the PyPANDA API in general. So here we have this make recording script, which is the Python script that will make a recording for us. And let's just look how simple it actually is. So we can see here that it imports this Panda RE, which corresponds to the, if we go into the Panda main repository, we can see that that corresponds to essentially the Python code that exists within this folder Panda RE. And then it does a few things. It first asks us for some arguments, that is mainly just the recording of the name of the recording. And then it creates first down here a Python object corresponding to this some Panda argument, where we tell it the architecture of the system that we want to emulate. And then we perform this run function on the Panda object. And essentially these 2 are the only ones we need to perform a recording in Panda. But we have this decorator right here that essentially defines how we're going to control the recording. So we can see here that this call right here, record command, it tells essentially the Panda system that the recording should issue a command. So it should perform a command where we execute the program bash.upx, and then, this command right here, where we echo hello world in the bash by way of the bash.upx binary. It also has this parameter copy directory, which essentially copies a directory from our host system into the client system, into the guest system that we are emulating. And in particular, we are copying this to move folder. And if we just look at what's in the directory, we have the to move folder right here. So we need to run we need to run this make recording script from in here, and it will then move this folder from our host system into the guest system. And it also has this parameter right here that is called setup command. And this setup command will not be part of the recording. So this command that exists right here will be run on a Linux terminal inside of our guest before we actually start our recording. And what happens here is that we run this upx command from inside of the to-move folder, and we can see that there exists this file right here called upx, which is the one we will run before we do our recording. And what we will do is we will give two parameters, or like we will give one parameter to the command, namely the binary that exists in bin/bash, and then we will output whatever result we get to bash.upx. So what this setup command will do is it will pack the bash binary and put it into a another file, and we'll put the packed version into a file called bash.upx. And then this is exactly what we are going to record an execution of when we do our actual recording. So we can see here that we actually, so this right here is the normal UPX binary that you can use to pack executables. And we are then going to pack the bin bash command and output it to bash.upx, and then we are going to record execution of a packed version of this file. And the main point here is that we actually need to pack an executable in order to display that the unpacker actually works. And in this case, we are simply going to pack the bash binary, so a shell binary, and then we are going to run it afterwards. And in order for bash to actually execute this command, well, it needs to unpack itself first. And we also give the name of the recording, which in this case is simply the name that we gave to the Python argument here. So that's how this, and then we have this call end analysis. So I'm not going to go into all of the details of PyPANDA. I will simply go over the examples and then hope that you will catch up how PyPANDA kind of eases some of the aspects of this whole interfacing to Panda. But we can see just from these scripts, it's actually, from this script right here, it's very simple to perform a recording and also do various, say, sophisticated elements with the recording, namely copy a directory from the host system into the guest system, running commands in the guest systems, and also controlling the recording that we will do. So essentially, this is the key aspect of the recording, and a lot of this other stuff in the code is kind of like just boilerplate around it. Thus, it is the core details is extremely simple. Now, once we have done the recording, we need, in order to do the unpacking, we need to run this pyunpacker.py script. So now let's look a little bit at how that works, namely the one right here. So first we can see that this script also takes a few arguments, namely the recording name, as well as the program name, and then it also takes something called granularity here. And this recording name will simply be the name of the Panda recording that we have made. And this program name will be the name of the process that we are looking to unpack in a given recording. Now, from a high-level perspective, what this script does is it creates a Panda object, and then it performs a replay of this recording that the Panda. It performs a replay of this Panda object where the recording it will replay is the one that we have given as an argument here. So recording name and recording name here. But during this replay, it has registered two callbacks. It has registered a callback here that is to the Panda callback that will be called whenever the asset changes. And asset here is address space identifier. So that's something whenever the address space identifier has changed in the system, in the recorded system, this callback will be called. And the address space identifier is essentially something we use to identify which process is executing in the guest system. So here we will see what is the old asset and then what is the new address space identifier. And we can then use this interface in PyPANDA to get the process name in this, so like the environment that we are executing, that we are recording. And we can use that. So here we have a callback in, or like an API exposed by PyPANDA that will do, first it will it will call into the Panda reverse engineering framework, and then that will interpret everything that goes on in the guest system in order to extract the name of the process in the, say, recorded emulated system. So simply this API right here, a huge amount of stuff will go on just in order for us to get as a Python object, the string name of the process in the recorded system. And we can use that essentially to match the name of the process with the argument, the program name that we gave as an argument here. So here we do this check on whether the process that is executing, by way of looking at whenever the address space identifier changes, if it matches with the program name that we gave as the one we wanted to analyze. And then we set this global variable asset to check, which is defined here. We set that to be the asset ID, so the address space identifier in the current process. So this callback is used to match the name of the current process in the recorded system and then capture the address space identifier so we can use it in this callback right here. And this callback, we can see that it's these callbacks are essentially just created by using these decorators in our Python script. And then we have this callback that will be called before each basic block execution. So callback before block execution. And it takes 2 arguments. So this is a callback that Panda provides, that PyPANDA provides, and the 2 arguments here corresponds to the a struct called CPU state, which is essentially an internal sort of QEMU struct that can be used to extract a lot of information about the system that we are analyzing, as well as I think this is as well as a second argument, but in this case we are not going to use the TB, so let's not go into details with what that is. But then what happens in this call is we will first check what is the current address space identifier, and we need to use this CPU argument here, and if it is the address space identifier that we set up here, so that we set right here, then it means this is the process that we actually want to analyze. So here we have this correlation between we match the program name with the one that we are interested in, and then we set the asset to be the one asset of that process to be the one that we want to analyze, and then we can use it down here to verify that in this before each basic block, whether this basic block that is about to be executed is part of the process that we're actually interested in. And then we also have another PyPANDA API here where we check is the system in the kernel, and we especially want it to not be in the kernel. And then we also check if the block number is above the args granularity argument, which is the one that we also provided here. So essentially, if these 3 conditions are valid, namely it's the process we are interested in, we are not in the kernel, and the basic block number is above a certain granularity, then the next thing we do is we execute the code in here. And most interestingly, we call this function read all process memory. And what this function will do is it will read all the process memory of the process in the recorded system and extract it as a Python object. And then we go through this memory and we essentially calculate the entropy of all the memory. So here we do this, we create this entropy variable here. This is probably a function somewhere in our, it's an entropy function from SciPy. And essentially we just take all of the memory from the process and create this pk variable here, which we will be using to calculate the text entropy. And then we append values to the lists y-axis and x-axis and y-axis, which are ones we created up here. We append the guest instruction count, so the number of replayed guest instructions in the system, and the entropy of the memory. So here we create this x and y coordinate that will be part of this graph right here. So we have the instruction count as well as the entropy variable. So here the entropy, where were we? So here the text entropy, which will be the y variable, corresponds to the value that will be put on the y-axis. And then the x-axis here corresponds to the guest instruction count, which is the ones that we will see, right here. And the next thing now for us, and just to clarify what these x and y-axis list does here, these are essentially shared variables with the web server. I'm not going to go into the details with the web server because it's not really that interesting, but the x-axis and y-axis are shared to a web server that will display this graph in real time. And then what we have is it would be nice to just check how this function works, read all process memory. So let's look where that is. And that function exists within the utility module, which we have right here. So let's look at the read all process memory. And we can see that what this function does is essentially just just perform various calls on the Panda object that is being passed to the read all process memory. And in particular, it gets essentially just all the virtual memory of the process that we are analyzing, and in particular, it gets of the currently executing process on the system, and it determines which process is existing on the system, currently executing on the system by the CPU struct, and this is all the virtual memory that is accessible by way of the operating system introspection plugin in Panda. And this, just to clarify very explicitly, this may not be all of the virtual memory that actually is in the process, but just it is still kind of like it is constrained by the core Panda tooling as well. Okay, but what's important to realize here is that we can essentially extract all virtual memory from a given process with just two very few lines of code where we use the API's get mappings as well as read virtual memory read. So it is extremely simple to develop a small tool, or to develop a tool that extracts all of the virtual memory for a given process, and that in itself is very powerful. So now what we should do is we should look, before we move on to the demonstration, we should just look at one last thing, which is this transition aspect from this unpacker into Ghidra. And if we look at the web server, we have this call down here that is a function that is called selection. And essentially what this selection function does is it will create the web server will create this table, and then it will allow us to click on each of these blue dots. And when we click on one of these, this selection function will be triggered. And the main thing that this selection function will do is it will create a new process where the entry point of the process is do transition to Ghidra. And it will, in particular, it will give this value as an argument, and the value will correspond to the x coordinate of these blue dots, namely the instruction count of the replay. So if we look at where this do transition to function is declared, it's declared within the Ghidra integration module. So let's look at that, and then we have that right here. And we can see that the Ghidra integration is, say, 50 lines of code or something. And it is extremely simple in that it will essentially just populate Ghidra. So what we have here is it will first, okay, so what it will do is it will perform a replay of the Panda recording. So it creates a new Panda object here, and it then performs a replay of the Panda recording, but it then has this callback on before block executions where it checks whether the instruction count in the guest system is equal to the instruction count that we provided to the argument, namely the value that we provided here that corresponded to the instruction count right here. So it's extremely simple in terms of it performs a replay, and then it performs a replay until we reach that instruction count, and then it calls this populate Ghidra function. And this populate Ghidra function that exists right here, essentially what it just will do, it will take the current program of Ghidra that is opened in Ghidra, and it will use that to put all of the memory from Panda into that Ghidra session. And first it will delete all memory segments in that program, so we will just erase everything that exists within the Ghidra analysis, and then we are going to read all of the memory in the Panda system, and we are going to, by way of this mappings that we saw before, and also the read memory function, which is another one that exists in the utility, it will then call this set bytes function on this Ghidra current program, which is part of this Ghidra bridge, which is another tool that's not part of PyPANDA, but it will essentially just set all bytes in the Ghidra program to all of the bytes that exist in the Panda process. Okay, so now we have gone through the entire process in a very very condensed manner, in a very quick pace of how this whole unpacking system works. We have looked at how it, how we do the recording, how we analyze the entropy by analyzing the virtual memory of the process in the recorded system, and how we then transfers all of the memory from the process in the recorded system. We transfer all of the memory from that process into Ghidra at a specific point where the entropy of the process is equal to a given value, and this value is one that we can then determine ourselves. We can pick one of these spots, and then that will transfer execution into Ghidra with the memory as it looks at the given instruction count. Okay, so I hope that was I hope you could follow that, as it was a little bit condensed, but now we're going to try it out and see how it is in practice, and then we're going to take it from there. Okay, so now let's go through the example that exists within the BART 2021 repository in the Panda umbrella repository. So we will simply issue the commands that exist in the main repository and show that you can build the system by way of simply doing that. So we are in this directory PyPANDA, and let's just clone it as follows. And then issue simply the commands one by one. And we also want to build the Docker image as follows. And then we can create a directory called out. And then we are going to run the demo. But before we actually run the demo, I would like to run it with a little bit of a different element, because we need to open a few ports as follows. So the main difference here is that I provide these peek commands, and I will also provide this flag net equals host. So this is the exact same command as that is indicated right here, with the main difference that I also give these arguments. Okay, so let's run those. And then we are now inside of this of our Docker container. So we have these 3 folders that corresponds to these 3 folders. This unpacker here. And then what we're going to do is we are going to do the unpacking example. So let's go into unpacker as follows, and then we will run this Python make recording bash as follows. And what you see here is that there is this Panda, so PyPANDA will download these prepared QCOW images that we can use to perform our recordings. And well, as we can see, this is provided by MIT Lincoln Lab, I think, but it's going to take a while to download this. I will resume the video once we have completed the download and the recording has begun. But main point is you can actually get, they will download these QCOW images for you, so you don't have to prepare any kind of virtual machine in order to actually do these recordings. Okay, so it just finished now, and it took a while to run the command. We can see that here we have this downloading of the image, and then we have the running of the various Python, so like the output from the PyPANDA command right here. And what we can see is we have this bash. So we essentially have the 2 artifacts in terms of the snapshot of the process, as well as the log of non-deterministic input to the CPU. So I'm just going to run it again, where we don't have to actually analyze when we don't have to download this Linux QCOW image, and I will just call the recording something different this time. So Python bash 2, and we can see that it goes much faster now. We see output from PyPANDA in terms of what are the arguments provided to the PyPANDA, so like PyPANDA logic. And essentially what it's doing now is that it's running our setup command in the system that we are doing a recording of. So we can see that we have this, we already went through the commands, namely it runs this UPX command inside of the system that we are recording. So this one right here is the setup command. And if we remember in the implementation, that corresponds to this exact bit right here, the setup command here. And then it does this, the output here we can see is the output that corresponds to UPX. And then afterwards we do the echo command. Then we perform this. Then we run this bash upx where we echo hello world. And it seems like that is not being output to the terminal. So specifically, we don't see this output to the terminal. But what we're going to do now is we are going to continue the example. And we're essentially going to run this Unpacker module now. And what we're simply going to do is we are going to run Python unpacker, unpacker as follows, and we want to have bash 2 because this is the name of our recording, and then we want to have granularity. We can also just follow actually the example that was written here. So as follows: Python unpacker bash granularity, and we want bash 2 here instead of bash no bash followed by nothing, because this is the name of the new recording. So let's run this. And then what we're going to see is if we go into this URL, we can now start to see we should be able to see now you see this logging in terms of entropy on the y-axis and instruction count on the x-axis. And it looks a bit funny this right now, and that's just how it looks. A lot of overlap in terms of the text here, but essentially these are the various stages during the program execution where we have the entropy of the data in the virtual memory of our process, and here we have on the x-axis the various instruction counts. So we're going to click on one of these, but we need to open up Ghidra in order to actually be able to transfer this virtual memory to our into Ghidra. So we're going to open a new instance of Ghidra. And I'm simply just going to call Ghidra run here. And notice that I'm going to now rely on this Ghidra bridge tool. And the only thing you actually have to, I'm not going to go through installation of that, but the only thing you have to do is essentially these 3 steps. Once you have done these 3 steps, you will be able to do exactly as what I'm doing now. So I'm going to click close, and then I'm just going to take a random file here. So this can be anything. It doesn't have to be anything specific. And I'm going to say we don't want to analyze anything at the moment. Let's just say no. I'm going to put it over here to the right. Let's make it a little bit bigger. And then what I'm going to do is I'm going to go to Tools and Ghidra Bridge. And this possibility, you're going to see that once you have done these 3 steps over here. So we're going to say run in background. And now Ghidra Bridge is running. And now we will be able to click on one of these, and it will transfer the data of the process over to Ghidra. So let's see what's happening right now. Let's click on this one. And we see that something is happening down here. And essentially what you will see is all of this being reloaded now. And it will be reloaded with the data from this memory. So now you can see all of the memory is being populated in Ghidra. And this corresponds to the memory of the process in our recorded system at this replay instruction count. And we're going to see a lot of stuff, and essentially all of this corresponds to the unpacked version of the bash script. So remember that what this example essentially did was it packed bash. If we go into unpacker and if we go into make recording, essentially what it did was it created this packed version of UPA of bin bash, and then we outputted that to bash.upx, and then we ran the packed version. So here we will have most likely at this stage in the program execution, most likely the bash.upx will be unpacked, so we will have an unpacked version. But it's a little bit difficult to actually verify that we have an unpacked version of bash. So instead, I'm going to create an application where it's extremely simple for us to actually recognize that the binary is in fact unpacked. I've prepared this small application, which is essentially a script. So what I'm going to do is I'm going to change first I'm going to close this script inside of Ghidra, inside of our Docker container, sorry. I'm going to go into this to move folder. Then I'm going to create this small Python script called p1py. And I'm going to, we need to have Vim as well. So let's just install Vim right quickly. And then I'm going to create this small Python application. And the only thing this Python application does is it creates the top of a C file, and then it prints out 3,000 print hello statements. And these hello statements each will contain a unique integer. And this will be in a function called T1. And we then have a main function here that calls into T1. And essentially we just output all of this very simple C application to stand that out. So we're going to run this tool p1py and output it to, let's call it ex1.c. Okay. So now we have an application here called ex1.c, and what we're going to do is we're going to compile this ex1.c, and we want no optimizations, and let's just output it to unpacked, or let's say clean. Okay. So now we have this small application, C application, that will simply print out a lot of these strings. And the reason I do it this way is I want to have a program that is very easily recognizable once it is unpacked. So we are now going to change the script in the make recording to, instead of packing bin bash, we want it to pack our clean binary. So if we say here, let's say bin/clean, and we can just output it to bash.upx, similar, because then we don't have to change other parts of the script. So let's just do as follows. So now we run upx on our clean binary, meaning we compile this simple we pack this simple C application we just created, and we output it to bash.upx. And then we, in our recording, we will execute the same program, which is now our simple application. And the idea is here we can use this setup to actually make it a little bit easier for us to verify whether we can then see the instructions that corresponds to these print hello statements. And overall, the idea is just to make it very easy for us to actually show that this unpacker works. So let's run the make record script again with a new bash here. So we will output it to a recording called bash3. Oh, we need to make the recording first, as follows. That looks good, and it's running now, and something went wrong. And what went wrong was because I put in a wrong name. We don't need to do bin/clean. What we need to do is to move/clean, because the clean binary will be in the to move directory. It's this one right here. Okay, so we will run it again, and this time let's just do bash4, and it seems to be, hopefully it will run this time. And we can see that now UPX is indeed running. So we got the output from UPX that shows that indeed the packing of our simple binary did progress. And then what we're going to do is we are going to run the unpacker again, and we are going to connect it to Ghidra again, and then we are going to see we're going to look at the memory and see if we can actually find our code. So now we're going to say, remember that we did this to bash4. So what we're going to do is we're going to say PyUnpacker as follows. PyUnpacker, and we want to use the bash4 recording. So that's happening right now, and we move to our UI here, which is the Unpacker UI, and we will simply say reload it, and now we should start to see essentially new output coming out to us. Maybe we have to reload it again. And we can now see that it started to run. And in this case, we got a little bit less amount of print statements, probably because our program is a lot shorter than bin bash. And let's just click on, oh, we got a little bit more output here, but let's just click on one of these and then verify what's actually going on. So we click on it here, and it should get loaded into our Ghidra application. In a moment, we should see all of this be uploaded again. Sorry, updated with the new binary. And this is happening right now. Now our Ghidra bridge, so like the unpacker script, is throwing all of the memory from the process into our Ghidra instance. And what we can do now is we're going to say auto analyze a.out. So let's just throw all of the analysis on it. And this is also going to take a while, so I will resume the video once it has finished. Okay, so the analysis, the auto analysis is now finished. And essentially what we have now is a bunch of memory that we need to analyze in order to find our binary. But what we can do is we can look at all of the defined strings in the binary, and we go a little bit around. We can see here we get a lot of these hello statements, which are the ones we created for our simple C program, namely the C program that we actually packed. So if we double click on that one, we can see that it exists, or we can also just look at the address of it, and we can see that it exists within this memory address right here, F50000. This one F50004, and so on. So it will exist within this memory range. And we can see all of the strings we have. We have all of the various null terminated strings here. So we have hello2, we have hello0, hello1, hello3, and so on. And if we go to this area in the raw bytes of the, if we just look at the raw bytes of this memory area, so as follows right here, then if we go a little bit further down, we should be able to see some patterns where we have these instructions that call into the printf statement. And maybe we have to look a little bit more. So we can go here and we need to find this E8 call instruction. That's essentially the one we are looking for. Okay, so I actually found the place inside of this address memory range, namely FE88. And if we look here, we can see that we have a lot of instructions that start with, or we have a lot of these E888 instruction patterns. So if we take one of these E8 here, and we click on D to disassemble it, we can see that there's a bunch of calls. If we now look at the decompiled output, so where do we have the decompiler? We can see that we have here all of the calls to this printf function that uses all of these hello strings. And this corresponds to essentially the unpacked version of this simple C application that we created within this recording of our target system, namely the packed binary. So indeed, the unpacker succeeded in the sense that we used the recording. We recorded a packed application running, and then in the replay, we used the entropy analysis to show us when the entropy was low. We then clicked on that in order to get the state of the process at that given moment into Ghidra, where we could then look at the binary in an unpacked state. And naturally, it's still sort of like in many ways very raw, but at the end of the day, the unpacking succeeded in the sense that it showed us and where the unpacking had occurred, and also delivered it to us in Ghidra, where we can then sort of like continue to analyze what is actually going on in the unpacked binary. Okay, so that's it for this video demonstration of the unpacker. It was a bit condensed, but I still hope you enjoyed it and also learned how PyPANDA works. And there's a lot of stuff to PyPANDA. I really wanted to display an end-to-end process in terms of taking one of the examples in the paper and showing what the input and output is of this process as a way of demonstrating the actual powers that exist with PyPANDA. And remember that what we have done here is pretty tremendous in terms of doing a recording of a whole system analysis, recording and execution of a packed executable in that system, and then replaying it, analyzing the virtual memory of the process of one of the particular processes in that system, and then extracting the data and so like information about that data, namely the entropy of the virtual memory, extracting information about that and using that as a way of unpacking a binary. And this is pretty tremendous, in particular also that we could do it with just very few lines of code as we can see in this Unpacker script. So this whole like PyPANDA makes sophisticated analysis very much accessible to the user. And I think this is pretty fascinating, to be honest. But that's it for this demonstration. So, welcome to this short interview with Luke Craig. Luke Craig is one of the authors and maintainers of PyPANDA, and he is also the first author of the new academic paper that presents PyPANDA. We will ask Luke a few questions, mainly related to how Panda is as a reverse engineering tool, and then also how Panda is as an open source tool. Like those would be the two main fields kind of like that we will be trying to cover with this interview. Okay, so welcome, Luke. Could you just introduce yourself and say anything else that you would like to say?
Hi, David. Thanks for having me. My name is Luke Craig. I am a staff member at Lincoln Laboratory. I want to say right at the start, though I work for Lincoln Laboratory, I don't speak on their behalf. I might talk about some tooling or products today as a means of comparison to talk about Panda and PyPanda, but keep in mind that's my personal opinion and it's not reflective of an official position or endorsement from the lab.
Yeah, totally makes a lot of sense.
Yeah.
So what's your background before you joined Lincoln Lab? Did you have any kind of computer science education or?
Yeah, so I went to Rose-Hulman. I studied computer engineering and I got a minor in computer science actually.
Okay.
It's kind of interesting. My senior design project was actually PyPANDA. I worked with the lab as a co-op before, and I worked on this project for a full year in that context. And this is it's certainly been developed a lot since then, but I got a full education in PyPANDA in school, and I was very excited about that, which was, my alma mater did a great job of linking us up and helping that out, and we were very excited about that.
Nice. How long time have you worked with Panda more generally?
More generally, so when I decided that I wanted to go work at the lab as a co-op, I contacted a professor at Rose and said that I wanted to do a independent study in actually I wanted to do it in Panda. I knew this was a piece of tooling that they were going to use, so I decided to take the opportunity and work on it there. So for a semester before that, so it's close to 3.5 years now that I've been working on Panda in some capacity.
That's pretty cool. A long time now.
Yeah.
Okay. So let's get to the more formal questions. So first and foremost, I want to just lay out whether you use Panda in a professional context to carry out professional reverse engineering tasks. Is that something you do?
Absolutely. I use Panda and PyPANDA in professional reverse engineering tasks every day.
Very cool. So it is a mature tool that can be used for such things.
Oh yes, the original Panda paper came out in something like 2014. So it's the Panda. It's gone through several versions. The original Panda tool has come a long way, and it is a mature tool that can be used in professional reverse engineering contexts. And it is, not just at the lab, but in other places. Yeah.
Okay, thanks a lot. The second question I have is, could you talk about where you personally find Panda useful? And in particular, I'm interested how it compares to other tools, such as, for example, debuggers and scriptable debuggers and things of that nature. Where do you kind of place it in your workflow?
Sure. Typically, if I was going to look at something like a piece of malware, I might do some static analysis first. But at some point, eventually, you need some dynamic analysis involved there. And Panda is useful in that context because it is repeatable, it's whole system, and it's plugin based. So when I say it's repeatable, I mean you can take a recording and get a deterministic replay. You can analyze that. You can pass it off to a colleague. It's really useful if you have that sort of malware sample and it has some sort of network interaction, as often they do. There's a stage 2 or something like that. And if you can capture that just once, you will have that forever. It's self-documenting because it's this trace. So this sort of repeatable record and replays is available in other products. You can see it in Mozilla's RR in userland, but doing that from the whole system or from the hypervisor level is a lot more useful because it's less intrusive. Things like a debugger are going to actively change process memory to do do analysis or enable ptrace, so something that malware might pick up. Being able to do it at the whole system level allows you to look at interactions with the kernel better and look at interactions with other processes in case like your malware wants to inject itself into some other process and take it over. And the last point that I was going to talk about was plugin based analysis in Panda as related to other things. So you'd mentioned scriptable debuggers. I love GDB. I love a lot of debuggers. I use them regularly, but they're really not set up for the sort of analysis that you want to do at the hypervisor level with malware generally. So what I mean by that, I mean that the plugin structure that Panda provides allows you to first off write your analysis in C and do it and handle it in the process, which is many times faster than analysis that you would do in a separate process that's trying to ptrace or trace something else. It also allows you to set up analysis that's reproducible and sorry, not reproducible, but structured in such a way that you can use them as building blocks. So, for example, if you wanted to link various pieces of analysis together, you could take the operating system introspection plugin and the taint plugin and use both of them and look at things like tainted branches. So those are branches that use material from a tainted tainted data, and you could use that and look at the process that it's in and follow that through and use PyPANDA to export those sort of things to Ghidra. So being able to look at those things in a much more structured way than a bunch of scripts in GDB is a lot more useful.
Right. So it's a good point that it is designed to have this kind of like composed analysis, building block-based analysis, rather than say that was not a second thing. And I wanted to just ask there. So at the beginning of you said there first, the sharing is pretty important. Is that, or is that nice advantage? Is that something you do in your work? Can you actually do people like, hey, share this this kind of like trace and so on? Mm-hmm. So is it a collaborate? Like, do you use it in collaboration with others? I guess that's
absolutely. We share recordings all the time. In fact, cool. Brendan Dolan-Gavitt had written a website for RR Share. I think it's still linked to the original version of Panda. Mm-hmm. There was a point where plugins where the record format changed, but I believe there's actually still a website that he hosts that has all sorts of recordings of various pieces of malware that you could just go online and download, and there you go.
So Brendan is one of the maintainers and also one of the early authors of Panda, right? At least one of the early authors. I'm not sure whether he still
certainly one of the early authors.
Right.
Yes, and he's a professor at NYU.
Right. Okay. So that was a very good, rigorous answer to that. So the last thing I want to talk here about in terms of understanding Panda from a reverse engineering tool perspective is, so in the video we saw some a fairly complex example in terms of a general generic unpacker, but could you tell us a little bit about your kind of view into some of the more complex tools? So if you are thinking of what are the capabilities of Panda and you want to see kind of at the end of the complexity spectrum, so what are the tools that you find there?
Yeah, so there's a few sort of tools and integrations and plugins that I wanted to mention to get a sense of what you can really do with Panda. So one of the more interesting ones is a full system taint plugin that we've built and developed. It uses LLVM to lift the underlying host code to LLVM and does the taint on that level, so that you could do taint on any system on any particular architecture as long as it lifts appropriately through LLVM, which is most of them, and then you can apply taint through that there. We have operating system introspection plugins that are built into Panda that include Windows, Linux, and in addition to that, there's with PyPANDA we can use we've been able to integrate various other projects quite easily, including we've done stuff with Anger and moving from a concrete execution into the symbolic and doing something close to a concolic execution.
Yeah.
You just saw the Ghidra example. We've done integrations with volatility. And one of the more interesting integrations that I've seen recently was not one that we did, but one that was the subject of a Black Hat talk. So Marius Munch and Grant Hernandez did a talk at Black Hat last year, actually prior to our publication, on emulating Samsung's baseband, which was really exciting. And they did that with PyPANDA, and they talked about the speed increases that you see moving from Panda to PyPANDA versus handling that.
That's pretty cool. So it's also fair to say that some of these complex tools are achieved by way of all these building blocks. So it makes sense that they combine a lot to achieve. That's cool. And
absolutely.
And yeah, there's a ton of work in the introspection plugins. Translating the raw kind of like memory data into actual higher level data structures takes a ton of work to that. Okay.
Yes.
So I think we got a fair good coverage and an introduction to Panda as in a reverse engineering context. So I want to move now over to Panda as an open source tool. So just a short view into Panda as an open source tool. And first I want to ask is, how is Panda welcoming contributions from the community and from non-maintainers in that perspective? Is that something Panda do? And
absolutely. I'm sorry. Go ahead.
No, go ahead, please.
Absolutely. We love contributions from anyone and everyone. We just had a really interesting contribution from a student, I think it was one of Brendan's students, to include Z3. So as you track through taint, you can follow the constraints in Z3 expressions of conditions under which you take various branches. I believe I'm not misrepresenting their work, and then you can get a set of constraints under which you follow to a particular branch, and that was really exciting. And
so you can kind of extract the path constraints for that's pretty cool on a whole system level.
Yes.
Nice.
I'm not going to make any guarantees about performance,
sure.
but yes, you could absolutely. That is one of the things that was contributed quite recently, and we are very open to any pull requests or interest in the project. We have a very active Slack workspace that you can get to by going to our website panda.re and requesting to join, and very open. We've got lots of people in there that can help you with development or anything like that.
Do you have any I would assume that you probably have quite a few areas where people can contribute, also depending on one's background. Do you have any kind of could you say some interesting ones? Or
we love seeing really interesting plugins and integrations and use cases, and we love seeing better documentation and more usable documentation. I know that's the standard we're an open source project answer, but we try. And but the more people that work on documentation, the better the more accessible it is, because just because I write a sentence of documentation doesn't mean that everyone's going to understand it, or somebody new to the project might not. So it's really helpful to have more people doing that sort of thing.
So plugins and documentation, plugins applied, the plugins in a sense, use cases I really appreciate it. That's great to know. And if you are a student or just a programmer, so are there any kind of more formal ways that one can get involved? So for example, do you have a Google Summer of Code participation or internships or something like that?
The lab has internships, and that's traditionally how we've gotten people to work on that. That's traditionally how people have worked on Panda. I will say, you had mentioned Google Summer of Code. We don't have one of those, but I'm definitely going to take a look at that for next year. That is a really exciting idea. Yes.
Okay. So in order to get formally, you can get paid on working it if you land an internship. That's one way of doing it. Okay.
Absolutely.
And then perhaps also, since you mentioned before that one of Brendan's students did it, perhaps a more formal approach is also to ask your professor, and you yourself ask your professor whether you can actually work on that project, and you're happy to involve. That's pretty cool.
Yes.
Okay, so great. Panda is welcoming contributions from the community. That's awesome to know. Okay.
Absolutely.
So I think that's it for this interview. So I want to thanks a lot for joining, Luke. And
Mm-hmm.
well, PyPANDA was an awesome thing to work with. I really enjoyed going through it, and I'm pretty fascinated by what you can do with Panda and PyPANDA.
Thanks for having me. Yeah, very excited to talk about it today. Thank you.